Okay, so the first thing that I'm going to do is just give a little bit of a review of what we did last week. So we started lecture set number 1 after going over the course outline. So far in lecture set number 1, we've been discussing the model fitting process and we've finished the second step. So the lecture set begins with the general definition of a regression model. So for our purposes throughout the course, we're really going to be focusing on the case where we have a univariate response variable. So we'll have n observations of one single variable, and then we're going to have a set of predictors or explanatory variables that we call x, and our goal is to link those explanatory variables to the response. The function that we are going to use throughout the course is the linear function. So we're going to see countless examples of how to link the response variable to a linear function that's defined in equation 1. What's going to change for us is the assumption that we place on the response variable. So right now we are reviewing the linear regression model where the response variable or the error terms in this situation, given the formulation of the model, are normally distributed. So that is, they exist across the entire real line. And when we have a response variable of this type, it's very common to use a linear regression model where you assume a normal distribution for y. There's a lot of different reasons for this. One of the most attractive reasons being the mathematical familiarity of this distribution. So that is, the normal distribution is something that people understand, or as statisticians, we have a good grasp of. We know how to check the properties of the normal distribution. We have a good idea of what we're looking for when we say something is normal. But as we progress through the course, we're going to work ourselves away from that comfort zone, and we're going to look at situations where the response is no longer normal and talk about how we can adapt this linear model to account for that lack of normality. All right, so we introduced the general regression model. We looked at a special case, SLR, looked at some properties, and then we started talking about the model fitting process. So this model fitting process is really what we're most interested in. And this is the focus of the first assignment. So we start off by specifying the model. This, for the first assignment, will be very straightforward because we're going to just be using a linear regression model. So we're going to have something of the form y equals a set of predictors plus that error term. The predictors are going to vary depending on the data set that you were sent. Note that I sent those data sets out after class on Thursday. So each student should have received their data set, which is not necessarily a modern data set, but it's one that is well suited for linear regression analysis. And all of them are available and readily available in R, which is helpful because we don't have to worry about loading them in and things like this. Okay, so the first step is specifying the model. The second step is estimating the parameters. This, from a computational point of view, is also very straightforward because R is going to do the fit for us. That is, R is going to compute our estimates of the linear model parameters directly. So we will get our slopes and y-intercepts, estimates of variance, etc., from the machine. However, we did look at an example of how we could directly fit the model by hand if interested. So we derived last class, or looked at the steps of the process of deriving estimates for the model parameters using the maximum likelihood approach. You can also derive these model parameters using the least square estimates. So in the case of the linear model, the least square estimates are a very common the method of least squares is a very common method for deriving the parameter estimates for the linear model. And it actually works out that they are identical to the maximum likelihood estimates. So these two processes, the one that we went over last class that's shown on slide 12, and the method of least squares, are going to return the same result. And I encourage you on slide 14 to review that process. that is just to review the method of least squares, and you can compare beta 0, the estimates for beta 0 and beta 1 directly to show yourself that they are the same, instead of just taking my word for it. Okay, so today what we're going to do is hopefully finish lecture set 1. Now there's 2 steps left in the model fitting process. So again, we have formulation or specification, which is just stating the model that we are going to work with. Then we have the model fitting process, which can be done through a variety of methods. In this class, we're going to see a lot of methods based off of maximum likelihood estimation. But again, for the linear model where we have normality, we could also use the method of least squares. Steps 3 and 4 are model assessment and inference, respectively. So on slide 11, I wrote out some of the processes that would be involved in model assessment and inference. I think that model assessment is probably one of the most important steps, if not the most important step in the process. Certainly model assessment and inference are going to be the key aspects of what we're interested in. Well, I should say, certainly these last 2 steps are going to be the most important steps, because inference is where we build conclusions and interpretations based off the model, and then we can use these to communicate our results. And model assessment is where we effectively, let's say, mold or work with the proposed model to find the best fitting model. So we can use variable selection, we assess our diagnostics, we make sure that the model we have formulated and proposed actually fits well, so that we can trust the results that we get from step 4. Actually, kind of an interesting story on that note. I was talking to one of my former master students yesterday, and he works as I think his role is like machine learning specialist, I think is the title at U of A now. And he was saying that he had this project, it was very open-ended, and he had fitted a regression model, and then he did like neural networks and support vector machines to this data set. And then he presented all the results to the chair and the dean, and they're like, yeah, we're going to use the regression ones because it's so hard to interpret the results from the other models. So the point just being that sometimes simplicity is the most preferred, but you still want to make sure that it fits well. Okay. So we're going to talk about these last 2 steps today, model fitting or model assessment and inference. We're going to look at model assessment in quite a bit of detail. So we'll review residual analysis, the different types of residuals, how we can use the residuals, and we will review diagnostic measures like the R-squared, DFBETAS, DFFITS, Cook's distance, so that we can assess the observations in the data set as well, based off of the fitted line. And then we will broadly paint a picture of what kind of hypothesis tests you might be interested in using. You might be interested in running given your model is fitted and fits well. Of course, the inferential part of it is very broad, depending on what you're actually interested in, whether it would be relationship between the explanatory variables and the response, or a study of the predicted values directly. There's a lot of different types of intervals or hypothesis tests that you can construct. And I'll sort of refresh your mind on what some of those are, but we won't look at those in a lot of detail because, again, for the most part, R will produce those for us. The same way as the residual analysis, but we still have to be able to interpret what we're looking at with the residuals. All right, so what is a residual term? Well, basically, it's just the difference between the observed quantity of Y in the data set and the predicted quantity of Y given the fitted model, right? So it's just the difference between these 2 points for a given value of X. In the situation where we're fitting an SLR model, the residuals are very easy to digest because you can plot them directly, and it's a comparison, and the value of Y hat is found simply by the value of Y hat is found simply by plugging in the observed value of X into the regression line. This would also be true for the MLR model. However, you might argue it's slightly more complicated because you're considering a set of X in the fitted model rather than one value of X. you're considering a set value, you're considering set values of the explanatories for each observation, all being plugged into the fitted MLR at the same time, rather than just the individual value of X. Realistically, it's the exact same process, but you're talking about one value versus K values essentially. Okay, so the residual values are effectively estimated, or the residual values estimate the model errors. So when we fit a linear regression model and we assume a normally distributed response, we have that plus epsilon term that's tagged on to the end of the model. We assume that epsilon term is normally distributed with mean 0 and constant variance. The residuals are estimates of these error terms. So therefore, we can use the residuals to assess whether or not those model assumptions are intact. So from that point of view, the residual analysis is very important because it gives us a direct method, or it provides us with a set value, or it provides us with set values that we can use to actually assess those assumptions directly. Now, the residual given on slide 15 would be considered the standard residual. So this is just the direct difference between Y and YI hat, but there's actually many different types of residuals. So for example, you have the standardized residuals. These are simply the standard residual values put onto a scale of 0, 1. You have the internally studentized residual, similar idea to the standardized residual, except that the way that you're standardizing it is slightly different, and you would expect the RI value to follow a T distribution. You have the press residual. The press residual is sometimes called the deleted residual. So the E subscript bracket I means that you are computing the residual by removing the ith observation. So the idea here is that the press residual is going to give you is going to be utilized to determine the effect of the observation that you were deleting. So you should see, for example, a drastic difference between that value and the other ones if that particular observation is like an outlying point or a point that's drastically different from the other observations in the data set. And then you have the externally studentized residual, TI. This is a similar idea to the internally studentized residual, except that you're using a standard deviation that removes one of the observations in the data set. And the externally studentized residual, again, would be a T distributed value, and you can actually use this residual to test if a particular observation is an outlier, and you can conduct that test with a statistical significance. So you can run a formal test about that particular observation using the externally studentized residual. Okay. In general, each of these residual terms can be used to validate the assumptions placed on the errors. So you should see a consistency across the shape of the residuals. So if you have that expected sort of cloud-like shape of the residual values, that should be consistent across all of the residual types. If you have some sort of funneling or curvature, that should also be consistent across the residual types. So they should show violations. They should all show or give evidence of a violation or give evidence of a lack of violation. So there would be an agreement, and therefore using these different type of residuals is kind of like a built-in check where we can assess the fit of the model and have some certainty that if this looks good and this looks good and this looks good, you know, we can say that perhaps the normality assumption is intact or the variance assumption is intact, etc. As I had mentioned on the previous slide, some of the residuals do offer different insights. So for example, those deletion residuals where we're removing an observation, those can also be used to give us an idea of whether or not a particular observation in the data set would be an outlying point or an influential point, which we'll talk a little bit more about momentarily. Okay. Okay, so in terms of expectation of those different residuals, we can write down some of the properties that surround the residuals so that we know what to expect when we are studying them. In every case, we're going to expect the residuals to have a mean of 0, which is consistent with what was given in the original statement of the regression model. In most cases, we're also going to expect the errors to be consistent. However, in some situations, like for the deletion statistics, this isn't going to be the case. And I'll show you what I mean momentarily. Okay, so starting with the standardized residual, first off, we can write that the sum of these residuals is also going to be equal to 0, which is consistent with the standard residual. And it makes sense because these are simply just scaled standard residuals. So the sum of the DI will be equal to 0. We can also show that the expected value of the DI will be equal to 0. And we can show that the variance, oh, sorry, I'm missing one part here. For I equals 1 to n. And we can show that the variance of DI is equal to 1, or rather, sorry, 1 over the average of the variance of the DI is equal to 1. And all of these proofs you might have gone through in Stat 378, sort of at the discretion of the advisor, of the teacher. It's not necessarily crucial that you actually show that these things are true, but they're not overly stressful proofs either. Basically just manipulation of the expected value and variance operators. For the externally studentized residual, or maybe it's just the studentized residual, internally studentized residual, we have that the expected value of Ri is again equal to 0. And we can show that the variance of Ri is equal to 1 for I equals 1 to n. So for the press residual, we can show again that the expected value of I is equal to 0, and that the variance of the expected value of I is equal to sigma squared over 1 minus HII. For the HII, I'll define in a little bit, but they're basically just the diagonal elements of the hat matrix. So you can see in this case that we don't have a constant variance. So the variance for the press residual is going to change for each observation. For the externally studentized residual, we have that the expected value is equal to 0 again. This one has a constant variance equal to 1. And we can show, actually, I'm going to make another. Okay. And we can show that the value of Ti can be written as Ri multiplied by the square root of n minus p minus 1 divided by n minus p minus ir squared. And this value itself follows a t distribution on n minus p minus 1. So again, the value of this is that we can actually write a formal hypothesis test about the value of Ti and use that to determine if there's evidence that that observation might actually be influential. Right. Oh, and then I was going to write this in the 5th step. So I'll just. So T is distributed TI given all model assumptions intact. And then the HII are called leverages. And the leverages, sorry, measure the distance between xi and the centroid of the data. And I'm going to come back to show some examples of the leverages momentarily. Okay. But the purpose of this slide is just to give you some idea of what to expect when you're studying these residuals. So that way, when you're plotting the residuals, you can determine if they meet the expected values and the variances that we have derived here. So it gives you basically some idea if there's a violation of those particular quantities. Okay. Again, the TI can also be used to construct a formal hypothesis test about a particular observation. And formally, the HII are what we call leverages. They're the diagonal elements of the hat matrix. High leverages typically indicate a value of X that's far from the center of the explanatory values. Okay, and we're going to look at a visual example of this momentarily. Any questions? Okay, so typically the first thing that we would teach or the first motivating reason for using residual analysis is to check the model assumptions. But the residuals can also be utilized to check if a particular observation is playing a role or has an influence on the model fitting process. Okay, so we can use a residual analysis, for example, to determine if a particular observation is outlying, if it has a high leverage, or if it is influential. In the case of the SLR model, we can visually assess if these observations are going to fall into one of these categories or into a variety of these categories. So what I mean is we can determine visually if we expect an observation to be influential, high leverage, or outlying. But once we move into the situation where we have K explanatory variables, so we're in a higher dimension, we can no longer visually assess the impact of each of the individual observations. So we have to rely on diagnostics built off of these different residuals in order to determine if a particular point might be influential, high leverage, or simply outlying. All right, so on this plot, we're going to visually define each of these different terms. So first off, this is a simple situation. So this is the situation where we fitted an SLR model. So this black line here represents y equals beta 0 plus beta 1 x. Okay. All right, now what this plot is showing us are the observations in the data set. And there's clearly 3 observations that are colored and meant to represent outlying or influential, n/or influential, n/or high leverage values. So there's the the red observation, the blue observation, and the green observation, or the circle, the triangle, and the diamond. Now, associated with each of these points is a dashed line. The reason for this is to help us better understand what we mean when we say a point is influential. Okay, so an influential observation is one that drastically changes the fit of the line on its own. So the idea here would be, imagine that the black open circles are the data. And then we're going to add in each of these observations separately. So suppose that we have the black open circles, and then we fit our regression line y equals beta 0 plus beta 1x. Now suppose that we add in only the red circle. The red circle is an example of an observation that has a high leverage because it is far from the center of the data. And it's an example of an outlying point because, or it is most likely an outlying point because it's also, 2 or 3 standard deviations, maybe 3 or more, let's be specific, 3 or more standard deviations away. Its value is greater than 3 standard deviations from the mean of the data set. Okay, so this red circle here is going to represent a value, okay, that is an outlier in the X space. So it is high leverage. Okay. Okay, so it's an outlier in the X space. So it's high leverage. It's far from the bulk or the median or centroid of the explanatory set, but it's not influential. And the reason that it's not influential is because you can see that the red dashed line and the black fitted line are not drastically different from one another. Obviously, this analysis is somewhat subjective, and we'll look at formal guidelines that we can follow to determine if a point is influential or high leverage. But in terms of visual definition, this is what we would expect to see if we have a high leverage outlying point that is not influential. Not influential doesn't change fit of line. Okay, any questions? Does that make sense? Okay, so the blue observation is also going to be high leverage for the same reason that we just discussed. So this will also be high leverage and outlying. But in this case, we would also write that this observation is influential because you can see that if you compare the black solid line to the blue dashed line, the inclusion of this point drastically changes the y-intercept and the slope of the line, or at least from a visual assessment appears to drastically change the slope and the y-intercept. Okay, so that's what we mean by influential. An influential point is one that changes, substantially changes the coefficients in the model. And again, we'll talk about criteria to determine if a point is influential, and we'll look at some of the measures that you can use to determine if a point is influential momentarily. But this is the visual definition of these terms. So this is influential because it changes the fit of line. Right. And then finally, we have this green diamond. So this is an example of a situation where we have a point that is not high leverage because its value in the X space is actually fairly close to the center of the observed of the open circles. It would still be an outlier in the Y space because it's quite far from the mean of the observed data's Y values, but not high leverage, outlier in the Y, but still influential because you can see that it again drastically changes the slope and intercept of the line. So this is an outlier in the Y space, not high leverage, still influential. Any questions? Okay, so we've talked about residual analysis to validate the model or to validate model assumptions and as tools for assessing the fit of the model. Now, when we're talking about assessing the fit of the model, we also have more common diagnostic measures that we can utilize, such as the R-squared term. In terms of using those residual values to determine the effect of individual observations on either the model fit or the predicted outcomes from the regression model, we're also going to look at diagnostic measures for those as well. So I'm going to come back to the point that I made a little bit ago. I'm going to come back to the point that I made a few moments ago about actual criteria for assessing if a point is high leverage, influential, or an outlier. In most cases, we're going to just look at diagnostics for each of these different quantities and then look at a criteria to determine if this is true. Okay, now just before we get there, we're going to very quickly review some more common diagnostic measures. Probably in the future, I'll just move this part around because it doesn't flow as naturally, but the most common diagnostic measure is probably the R-squared term, so the coefficient of variation. I'm sure all of you are familiar with this. It's essentially just a ratio of variance explained by the regression line over total variation in the response variable. So that is the SSR divided by the SST. Okay, the R-squared term actually results from what is called the simple linear regression model identity. The SLR model identity can be extended to the MLR model as well. Basically, all we're saying is that for a fitted regression line, total variation can be decomposed into two terms, that explained by the regression line and that explained by the error terms. Okay, so we have SST total is equal to SS residual error term plus SSR regression line. Okay, and this can be in either the multivariate or the univariate case or bivariate case, I guess you would say. SST is equal to SS res or SS error plus SSR. So we can summarize these computations in an ANOVA table like that given below. This is a particularly useful summarization because the F statistic from the regression ANOVA table can be used to test overall model fit. This is something that we'll look at tomorrow in lab when we actually review fitting regression models directly. And you can see from this table that the R-squared term is just a ratio of the regression sum of square to the SS total, which is also strictly stated on slide 22. But the point is that it's just a comparison of two sum of squares. So it's a proportion that assesses variation explained by the model. Right. Oh, and it's also worth mentioning, of course, that this R squared term is the square of the correlation coefficient. So we can directly get the correlation coefficient from R squared. The only thing with correlation coefficient is, well, one, it's used to assess the correlation between only two variables. So it has meaning if we're in the simple linear regression case, but once we move to the multiple linear regression case, there isn't, as far as I know, there's not a multivariate correlation. So you would be looking at comparison, linear correlation between all pairwise combinations of the response and the explanatory variables. This can be useful to us though, because you could create like a correlation matrix between all of the variables in the data set. And if you find explanatory variables with a high correlation, that can indicate multicollinearity, which, as I mentioned last time, is an issue with the model fitting process, specifically because we assume that the off-diagonal elements of the covariance matrix for the residuals are 0. Okay, the R squared, or the coefficient of determination, is a useful quantity for the SLR model. It's not useful in the case of MLR. In the case of MLR, the coefficient of determination will increase every time you add a predictor into the model. So as a result, you end up with a somewhat unreliable diagnostic tool because it's going to tell you that you have a perfect fit every time you add a predictor in. In fact, if you have one predictor for every observation, you will have an R squared equal to 1. Now, obviously, this is an issue for us because this is going to constantly tell us that the most complicated model is the best model. Furthermore, it's not reliable because we know that every time we add a predictor in, we're going to get an increased R squared. In order to deal with this, we develop, or we can utilize what is called the adjusted R squared. The adjusted R squared is fairly easy to understand. It's simply a ratio of the mean squared residual to the mean squared treatment. And we can use this in the same way that we do the R squared. So we can use it to kind of give, it has the same interpretation as the R squared value. So it explains, or it is a measure of variance explained by the fitted model. But it's also useful to us because if you have a multivariate data set, there are different model subsets that are going to exist within that particular data set, right? So you could have, let's suppose that you have y, x1, x2, x3. You could fit y as a function of x1 to x1 through x3. You could fit y as a function of x1, x2. You could fit y as a function of x1, x3. For each of them, you can compute the adjusted R squared, and it now becomes a means of comparing the models. So a higher adjusted R squared would indicate a better model fit. So in the case of MLR, the adjusted R squared is our preferred tool for assessing variability explained by the model, and it provides us with a way of assessing model fit when we want to compare multiple models across the same data set. All right, now returning to our previous study, or the definitions that we gave visually. We have this concept of an observation as being outlying, high leverage, or influential. In the situation that we are working with an SLR model, we can do things like plot the data directly and make visual assessments of the values. Of course, as statisticians, we like to have guidelines that we can follow, and even better, if we can, we would like to have formal hypothesis tests, such that we can say there's evidence at this point is an outlier, or evidence at this point is a high leverage or influential. Once we move beyond the bivariate case, so once we move beyond the situation where y is a function of just x, and say we're in the situation where y is a function of 3 or more explanatory values, visual assessment of the observations becomes more difficult. You can do things like use pairs plots to compare y to the different explanatory values, but oftentimes on most standard computer screens, as the complexity of as the dimension of the data set grows, in looking at those pair plots can become very difficult. You could like zoom in on each individual one and things like this, but at that stage, it's more efficient to use measurements based off of the residual terms in the data set and construct guidelines to assess whether or not a point might fall into the category of one or more of the categories of outlying, high leverage, or influential. All right, so I had mentioned before that the leverages, the HII values, are the diagonal elements of the design matrix or the hat matrix, X transpose I, X transpose X inverse X transpose I. I think I have an extra transpose here. I'm 100% sure I do. N by P, P by N, P by N. I think it's X, X transpose X inverse X transpose. So this should not be here. Okay, so large values of HII would indicate observations that have a high leverage and are potentially influential. So how can we work with these? Okay, well, in the situation that we have a high leverage that it exceeds 2 times the dimension of the data over n, so 2 times p over n, we can say that this point is far enough from the centroid of the design matrix to be considered a high leverage point. Okay, so the first rule that we can establish for determining if a point is high leverage is to say that any observation whose HII value, so any observations whose diagonal element of the hat matrix exceeds 2p over n would be considered high leverage. Right? Okay, now to determine if this observation is going to have an impact on the fitted model, we can use Cook's distance. So basically what Cook's distance is a diagnostic tool that will determine the impact of an observation on the fitted model parameters. Cook's distance is given on slide 28. So we have DI is equal to RI squared HII. So you can see here that we have the standardized residual term, internally studentized residual term squared multiplied by HII, which is the leverage or the diagonal element of the hat matrix again, divided by P times 1 minus HII. Okay, now this quantity is also particularly easy to utilize. Basically, what we are going to say here is that any Cook's distance that has a value greater than 1 would be considered influential. So we now have criteria for assessing model fit directly through the adjusted R squared. We have a criteria for determining if an observation is high leverage, and we have a criteria for determining if the observation is influential. Okay, so adjusted R squared, direct comparison of the leverages to 2p over n, and the Cook's distance measure, which we directly compare to 1. If DI greater than 1, we can consider it influential. We're going to talk about 2 other terms for assessing similar impacts. The first one is the DF beta. The DF beta term is also used to determine the effect of an observation on the model coefficients. So what the DF beta does, similar to the Cook's distance, is it deletes one of the observations in the data set and then studies the impact of that deletion. So in this situation, we have DF beta is the difference between beta j and beta j subscript open bracket I close bracket. So basically what this means is we're going to compute the model coefficients using all available observations, and then we're going to recompute each model coefficient by taking one of the observations out, and then we're going to standardize the difference between those. One of the things that you might be noticing at this point is that these diagnostic measures, in particular the deletion diagnostics, are really only valuable in our current computational age. You can imagine that trying to do this by hand before we had computers that could compute the fits for us directly would be very taxing, because you would have to continually repeat the process just by dropping observations out. Obviously, in those situations, you might use visual aids to check particular observations individually, but now we can assess all of the observations very rapidly, almost instantaneously, just through the click of a button. Right? To determine if a DF beta if an observation is influential via the DF beta calculation, we'll say that if the absolute value of the DF beta exceeds 2 over the square root of n, that observation could be considered influential. So we now have the Cook's distance and the DF betas as measures for determining if an observation is influential. That is, they are measures to determine if an observation plays a significant role in the calculation of the model coefficients. And then, of course, now we can determine if those two agree. And if we have agreements, it's more evidence that that point is influential. Okay, one other criteria following from the DF betas is the DFFITS. This term, like the DF betas, is utilized to determine the impact of a particular observation. The difference here is that we are now assessing the impact of that observation on the predicted quantity. Okay, so you can see from the formula, we have a standardized distance between yi hat and yi if we remove the ith observation. And in this situation, similar to before, we say if the absolute value of the DFFITS exceeds 2 divided by the square root of p over n, that observation plays a significant role on the could play a significant role affecting the outcome of the prediction of the regression line. So we could look at this as an influential point as well. Okay, the last quantity that I wanted to review is the COVRATIO quantity. This is a quantity that's used to determine the impact of the observation on the precision of estimation. So obviously we would like higher precision. So following from the definition given on slide 31, if the COVRATIO for the ith observation exceeds 1, we would say it improves estimation. If it's less than 1, we would say it degrades estimation. And we can also say that if the COVRATIO is outside of 1 plus or minus 3p over n, this point can be considered influential. So we have a variety of terms that we can use to determine if an observation is influential, regardless of the dimension of the data set. We can compare each of these different values. This is helpful because it gives us reassurance if one procedure picks up an influential point, but the other one does not. This could mean that there might be a discrepancy, but if they all agree, it's most likely an influential observation. And we can also determine if an observation is playing a role in improving the fit of the model via the COVRATIO approach. Okay, so that is the end of my review of diagnostic assessments of the fitted line. There's a few other points that I'm going to touch on briefly once I conclude this lecture set, but does anyone have any questions at this point? Okay, sounds good to me. Is equally valuable. Thanks, man. All right, so I'll just touch on I'll just briefly touch on the inferential part. So this is the last step of the model fitting process. When we talk about inference, we're typically talking about confidence interval construction and hypothesis tests. So this is using the regression line to ask a particular question about the data or about the population from which the data was sampled. On assignment 1, there's no particular set question that you have to answer. You're given a response variable, so you're free to explore the fitted model in whatever way you are interested in. If you simply want to assess fit of the model, that's fine. But if you'd like to take it a step further and assess predictive ability or assess individual observations influence on the line, this would also be welcomed. Some of the general tests that we are interested in would just be overall model fit and suitability. This can usually be done through the test of linear relationship. So in the SLR case, it's very easy to understand this test. It's essentially a test of whether or not X and Y form a linear relationship. And that's done by testing whether or not there's evidence that beta 1 is different from 0. For the MLR model, the test is structured by writing beta 1 through beta k equals 0 versus the alternative that at least one of the slopes is different from 0. This is more of an ANOVA style test. So this will give you evidence. When you run this test, you will be given evidence whether or not the overall fit of the model is useful, but that doesn't mean that every coefficient in the model is useful. And that's where the idea of variable selection and conditional hypothesis testing comes into play. And we'll talk a bit more about that in lab tomorrow when we look at the output from the R summary for the fitted line, because this gives you conditional hypothesis tests for each of the different values in the model, which can also be used as a very loose variable selection tool. Okay, so I've mentioned that term a few times. And again, I'll show you examples of this tomorrow because they're easier to illustrate empirically. But one of the other key aspects of the model fitting process is variable selection. So usually we start with a full model. We would assess that model. In some situations, the full model on its own might fit well, and that's great. In other situations, the full model might not have an adequate fit, and we need to start removing variables to try and improve the fit of the model. But either way, we're usually going to be interested in conducting some kind of variable selection for our fitted models, if for no other reason than to reduce model complexity. It's always ideal to try and explain the relationship between the response and the predictors using the fewest number of predictors that are possible. This increases interpretability, which increases understanding. There are multiple different ways of performing variable selection, especially in the case of multiple linear regression models where you have a large suite of predictors. Again, this can be done through conditional hypothesis testing. So if this value is not useful given the other ones in the model, this would be a valid reason to refit without that particular explanatory value. You could also use techniques like forward and backward selection. These are usually based off of the same criteria. So forward and backward selection are essentially going to determine which variables should be removed using the conditional relationships with the other values. You also can use things like the adjusted R squared approach to compare model fit across all of the different models. So this would fall under the all possible regressors approach. And again, we'll look at strict examples of this tomorrow. The key here is, again, we want to try and use a model that is, as for lack of a better term, that is as uncomplicated as possible to solve or to answer questions about a particular population. But how we arrive at that model doesn't have, there is no perfect process for getting to it. And this is sort of where I think the art of statistics comes into play. And you can explore the full model and the possible subset models in a variety of different ways. And a lot of the time, if you take approach A for your model fit and compare it to approach B from another person's model fit, if you arrive at the same answer, this is again a sort of a validation that the model you're arriving at is the best fitting model for the data that you are working with. You can also compare the different variable selection techniques like forward selection and backward selection and stepwise regression. And if they all end up at the same model as well, that can further be evidence that that particular model is the best fitting for that data set. Okay, so the variable selection process typically would take place somewhere between step 3 and step 4, in my opinion. But sometimes you can end up with a full model that fits really well. You can perform inference on the full model and then go and explore another model where you reduce the variable set. So it's sort of it's a situation where it doesn't necessarily fall directly into the model fitting process at any particular point, but you could sort of slide it in at a number of different stages depending on the process that you want to take for the data set that you are studying. And as I mentioned before, essentially what assignment 1 is a review of that model fitting process with variable selection included at some stage. So we will review how to do this in R in lab tomorrow. But this first lecture, the first assignment is essentially based off the concepts from this first lecture set, and which is a review of the concepts from Stat 378. Okay, so any questions? Okay, so that'll take us to the end of lecture set 1. So we'll start lecture set 2 now. Lecture set 2 is on the definition of a generalized linear model and the exponential family. So this is the first lecture set where we're going to see a formal definition of a generalized linear model, very similar to the linear model, except that we're basically transforming the response variable or the expected value of the response variable. I'll go more into detail on this as we work through this lecture set and we progress through the course. And more importantly, this lecture set is really focused on the definition of the exponential family. So as we will see, models that can be formulated within a generalized linear model framework response variables that can be utilized within a generalized linear model framework also belong to the exponential family distributions. So understanding properties of the exponential family is going to be useful to us because it'll help us understand properties of the models that we're working with as well. Okay, so in lecture set 1, the first step of our model fitting process was the model formulation step or stage. Okay, so this can be described in 2 steps. Step 1, we have basically specify an equation that links the response and the explanatory values. Okay, so for example, we might consider very basic model here. To beta 0 plus beta 1x. Okay. And then on step 2, we have to specify the distribution of the response variable. Okay. So that model that we had just specified on the previous slide, that's typically the choice when we are analyzing continuous data that exists across the entire real line, right? So I've mentioned this on a few different occasions now, but the normal, the assumption of normality for a response variable is most suitable when the observations are continuous values that exist between negative infinity and positive infinity. In this class, and I should also mention, like, as a result of that, the normal regression model, so the linear model that we've studied in lecture set number 1 is actually a subset of, or is one of the generalized linear models as well. In this class, we're going to focus on data where the response variable is univariate and the explanatory variables are multivariate. We will look at some illustrations where the explanatory variables are also univariate. So we're kind of like simple linear regression style cases as well. But for the most part, we'll focus on situations where we have variables, multiple variables of interest, and we're trying to find the combination of those that works best for explaining or for explaining what we see in the response variable. Okay. So most often, the assumption is that the response variable is going to be normally distributed. What we are interested in doing is taking it to the next step and saying, okay, how can I move beyond that normality assumption in the response to situations where it's clear that the response variable is non-normal? So that is the purpose of building generalized linear models. So generalized linear models are used to link a set of predictors to non-normally distributed random variables. Okay. Now, in this class, we're going to look at specific types of generalized linear models. In particular, we'll focus on cases where we have a response variable that is binary. So that is, we can model it using a binomial distribution. We'll look at situations where the response variable is a count. So we could model it using a Poisson distribution. And we will look at situations where the response variable is strictly positive and continuous. So in this situation, you would have a sort of like a truncated normal where everything is only in the positive realm, or you could use things like a Weibel or a gamma, some distribution that exists only in positive support. So we're going to study all of these as we progress through the course. But right now, what we're trying to do is just build the foundation. So we want to understand how these different distributions are related to one another. And we want to then understand how we can assess the fit of our model and then fit that model, those different types of models going forward. Okay, so basically what a generalized linear model does is it takes your traditional expression of a linear relationship. So we have the expected value of y is equal to some y-intercept plus a set of coefficient terms. And it utilizes what is called a link function, g, to link that explanatory variable, which is no longer normal, to that linear model. So the actual form of the GLM is really not all that different from what we have seen in Stat 378, or we looked at in lecture set number 1 for the linear model. It's just that now it's not a direct relationship between the expected value of y or y and the linear model. It's now a transformation of that expected value and the linear model. The result of this, while this might seem very simple, the result of this is actually fairly significant in that how we interpret the models changes drastically. And that's something that we'll focus on quite a bit when we study these models individually. So we still have a very interpretable outcome for the models, but they are not quite as straightforward as they were in the situation where we're just linking y to the linear model directly. Okay. So in equation 3, we just have a re-expression of equation 2 in terms of matrix notation, but it's the exact same idea. So a link of the expected outcome equal to the predictors times the vector of model coefficients. Okay, when we are modeling a response variable within the GLM framework, so as a generalized linear model, the response variables that are suitable for such a model also belong to the exponential family of distributions. All right, so any of the different types of generalized linear models that we will study in this class, each of the generalized linear models that we study in this class, the distribution of, for lack of a better term, the distribution of that generalized linear model will belong to the exponential family of distributions. So more strictly, the distribution of the response variable of interest has to belong to the exponential family in order to be used within the GLM framework. Now, there are exceptions to this rule. So from my understanding, there are other types of response variables that would fall outside of the exponential family, and you can make these work as a sort of pseudo generalized linear model, or kind of a an informal generalized linear model, if you will. But strictly speaking, for now, we're going to assume that the models that we study, the response variables distribution will belong to this family. All right, so when y follows or belongs to the exponential family of distributions, all that means is that its density function can be written as shown in equation 4 or as shown in equation 5. Okay, so we can fit, when we have y that belongs to some distribution, if we can show that the density function for that distribution also falls under the structure of equation 4 or equation 5, then we can say that that response variable belongs to the exponential family of distributions. Right? So for example, we'll start with I'm going to show you an example momentarily. Following the notation given in equation 5, so this is the notation that we will utilize in the following examples, we write that if a of y is directly equal to y, then the distribution is said to be in canonical form, which is another requirement of the generalized linear model framework. This is particularly helpful to us though, because we will derive the expected value and variance of the exponential family as a whole. And if the random variable is in canonical form, it means that we can directly compute the expected value and the variance for that particular distribution. B of theta is called the natural parameter. If there are other parameters in addition to theta, I'll show you an example of this momentarily. They are called nuisance parameters, and they can form parts of the other of C of theta or D of y, or depending on the structure of the distribution, A theta or B of y. Okay, so there's a lot of different distributions that belong to the exponential family. In fact, if you Google exponential family of distributions and you look at the wiki page, the table is very long, and it'll show you the different forms or how the different densities fall under this parameterization on that page. So just to give you an idea of how this works, we'll look at the normal distribution. So let's suppose that y follows a normal distribution with mean theta and variance sigma squared. Okay, so the idea here is that we want to write the exponential, we want to write y's density in terms of theta, and sigma squared here would be the nuisance parameter. So we want f of y as a function of theta within the structure given before. All right, so to do this, we're basically just going to restructure equation 6. So we can show that equation 6 can also be written as follows. So f of y given theta can be written as exp. Over negative y squared over 2 theta squared, 2 sigma squared, plus y theta over sigma squared minus theta squared over 2 sigma squared minus 1 over 2 log 2 pi sigma squared. Just wondering if maybe I skipped a few steps because I went right to the final declaration. Maybe just for completion's sake, I'll just kind of show one of the intermediate steps just so everyone kind of is on the same page in case you can't directly see what's going on here. So basically what happened is we pulled the exponent out front. After we pulled the exponent out front, you now have log of the leading term. Okay, and then we're going to subtract off this second value, and then all we're doing is expanding the inside this. Okay. So now it's a little bit easier to see. So you can see that the first 3 terms are basically just the second term from the first line, and I'm just pulling the negative 1 over 2 sigma squared inside of that quadratic. And then the negative 1 over 2 log 2 pi sigma squared. This is just a result of a log rule. So 1 over the square root of 2 pi sigma squared is the same thing as 2 pi sigma squared to the negative 1 over 2. And then when you log something to a power, you can pull the power down in front. So that's all that's happening there. then maybe actually I'll just, to make that a little bit more clear, I'll just directly write like this is 2 pi sigma squared to the -1/2, just so you can see it. Okay. Does that make sense? Any questions? Okay, so then recall what we're trying to do is get f of y into the following form: a y b theta plus c theta plus d. Okay, so therefore, we can show a of y is equal to y, right? So that's canonical form. We can show b theta is equal to theta over sigma squared. Okay. Then we can write that c theta is comprised of a couple of the nuisance parameters and some of the other terms. So this is going to be negative theta squared over 2 sigma squared minus 1/2 log 2 pi sigma squared. Okay. And then d of y is equal to negative y squared over 2 sigma squared. And again, sigma squared here is considered the nuisance parameter. So the exponential family is written as y conditional on a single value theta. It doesn't have, theta is a placeholder, like we could just write it in terms of mu here, but then the other value would be considered sigma. The other parameters, if applicable, would be considered a nuisance parameter. And it would actually be interesting. I'm not sure if you can do it. I'm not sure if you write the normal in terms of sigma squared and treat mu as the nuisance parameter. I don't think it would follow in the exponential family in that case. Just from looking at the form given here, I don't see that separation. Maybe you could do it. Y b sigma squared over sigma squared. And there would be additional terms. So in that case, I think c theta would be 0. You might be able to get a similar result actually. Right. Any questions? Okay, so we'll look at another illustration. Very similar logic to the first one, right? So here we would start off by writing f of y given theta, and then we have to pull the exponent out front here. So you're going to get log theta y minus theta minus log y factorial. Okay. And then from here, we can pretty much see that this particular one is quite easy. So you're going to have y log theta. There's your ay and your b theta minus theta. So that's one of your additional terms. And then you'll have the log y factorial left over. So in that case, we have ay is equal to y. So again, canonical form, b theta is equal to log theta. And then we have, log theta, c theta is equal to negative theta. And then we would have dy is equal to negative log y factorial. Any questions? Okay. All right, so let's stop here for today. And then on Thursday, we can start with one more exercise to go over writing quantities in the exponential family. We'll look at a few properties of the exponential family, and then we'll move on to diagnostics for the GLMs. So I'll see you guys tomorrow for our first lab. That'll be online, of course, but I'll mainly be using Zoom to broadcast the RStudio suite and how we would fit the linear model. So hopefully it's not too clunky. And otherwise, I will talk to you guys later. Have a good one. No worries.